In order to understand sinusoidal functions, we're going to start by doing a little investigation. I'm going to play this video and I'm going to ask you, how can we model the height with respect to the ground when going around a Ferris wheel? So for the first part, just follow this point, which is going around the Ferris wheel, and it's going to be creating a graph talking about the height with respect to time. And let's see what's happening. So we're following this point going around the Ferris wheel in a circular motion. And now we're just watching the Ferris wheel from a different angle because we're only interested in the height above the ground. And now using the height above the ground, we're creating this graph, which is time and what the height is at that specific time. What we notice is that as we're going around a circular motion, we're creating this oscillating pattern. This oscillating pattern repeats the same minimum and repeats the same maximum, and we seem to see that it's the same thing repeating time and time again. And this is what's called a sinusoidal function. So we're going to talk about the behaviors of a sinusoidal function, but in order to start talking about what is a sinusoidal function, we're going to go back to the study of circles and why is it important to talk about a point going around a circle. And let's, just to make it simple, make it a circle where we have a radius of 1 for the circle. And let's talk about where this point is after specific time. First, we're going to try and create a right angle triangle inside of our circle, where the hypotenuse of the right angle triangle is 1. With this hypotenuse of 1, now we have a triangle that's created, and we can talk about what would be the x side and the y side of my triangle. If we label the angle inside the triangle theta, then we can talk about our sine and cosine. So coming back to trigonometry, we have our sine of theta is equal to the opposite side over the hypotenuse side. We have cosine of theta is equal to the adjacent side over the hypotenuse. And then we also have tangent, but we're not going to talk about tangent in this video yet. So let's try and see if we replace the hypotenuse is equal to 1. We replace side x as the adjacent side because we're focusing on our angle right here. And then the opposite side is labeled as y. Now we have the sine of our angle is equal, opposite side is y, divided by hypotenuse, which is 1. And we have the cosine of our angle is equal to the adjacent side, which is x, divided by the hypotenuse, which is 1. So we get this really nice simplification where the sine of an angle is equal to y, while the cosine of our angle is equal to x. Now, why is this actually important? Well, this is telling me that if I focus on the y-coordinate of my point, any point going around the circle, the y-coordinate is going to be the sine of the angle rotating around the circle, while the cosine of that angle is going to be the x-coordinate of this point going around a circle. So we're able to go from angles to actual measurements, vertical or horizontal, as we're rotating through time. And that is where our sinusoidal functions are coming together. Now we're going to look at this simple graph of sine theta and then the simple graph of cosine theta, and we're going to see what these patterns look like. In order for us to graph sine of x and cosine of x, we first need to put our calculators into degrees. In this course, we're always going to be in degrees. Now, let's talk about sine of x. We said from previously, sine of x is going to be whatever the y-coordinate is around the circle. Now, let's think. What would be the angle necessary in order for us to go all the way around a circle? Well, that angle would probably be 360, right? So starting from an angle of 0 and then rotating all the way around to an angle of 360, we would have done one full rotation of sine. So let's go and see what the actual graph of sine of x looks like. And then we go into the graph. Now, the window is definitely not appropriate for this. So one trick that I can teach you for the calculator is if you go into zoom and then you scroll down to zoom 7 trig, well, this normally will help us with our window setting. So now we have a more appropriate window setting. I want us to focus on one rotation. So we're going to focus on only what is happening from 0 to 360. So I'm going to go ahead and change my window from, let's say, -5. So I'm adding just a little bit more, and 365, just so that we can see exactly what's happening. Okay, so using my calculator, I'm going to go trace 0, and I get that when x is equal to 0, y is also equal to 0. Then I can do the same thing for, let's say, 30. Trace 30, enter, and we get 0.5. So I'm going to continue, and I'm going to put these points on my graph below here. Then if I do trace 90, I get 1. Oh, I forgot to do trace 60. Let's try this one out. And we're just trying to get a feel of what these numbers represent, right? So something like this, which is a little bit higher. And what we notice is that if I do trace of 180, I am back to my starting point, which is y is equal to 0. So I have this pattern looking something like this, very symmetrical, right? It takes us 90 degrees to get to the top of the y, which makes sense. And then it takes us another 90 degrees to get back to our starting point. And then if I continue this rotation, I'm back at my initial starting point in terms of the y-coordinate, and then I'm going another 90 degrees, and I should be at -1 in terms of the in terms of the y-coordinate. Let's try it out. Trace of 270, I get in fact that I am at -1, right? Remembering that we're focusing on the y-coordinate when we're doing the sine function. And then if I do trace of 360, we should be back to our starting point, which is in fact when the y-coordinate is equal to 0. So this is the graph of a typical sine curve. Now what I want us to notice is that we're going to come back to this information here because we're going to compare a traditional sine curve to a traditional cosine curve. So in our calculator, let's go and put the cosine. So I'm just going to remove the sine for now, and I'm going to add cosine of x. Let's see what it looks like. So for cosine of x, now if we do trace 0, we are starting already at our maximum point of 1. If we do trace 30, so 30 degrees further, we are at 0.866. Trace 60, you're at 0.5, so 0.5. And then if we do trace of 90, so we go 90 degrees around our circle, we are at 0. Now, why is this? Remember, we are focusing on the x-coordinate. So when we start at an angle of 0, our x-coordinate is in fact 1. When we continue and we rotate around the circle, let's say we rotate 90 degrees up here, this coordinate is now 0, 1. So that's why the x-coordinate is equal to 0. And then we can continue like this and trace 180, so halfway around the circle. I am down to a minimum. And then if we do trace 270, I am on the x-axis, right? And then after 360, after the full rotation, I should be back at the very starting point. So this graph kind of looks something like this. What's super important is that both of these curves have the same look, right? Both of them are oscillating. They're just starting at a different position. And that's the most important difference between our sine curve in this course and our cosine curve. For a cosine curve, the y-intercept is always going to be either at a maximum or at a minimum. So right here, I'm at a maximum. Now, how do I get a minimum? That is going to be when the amplitude, and we'll come back to this just in a few minutes. If my amplitude is negative, then that's when I'm going to be starting at a minimum. And what does this mean? If I go onto my graph and I now have a negative cosine of x, let's compare what's happening now. Negative cosine of x, that is the black curve. So this black curve has a negative amplitude, and maybe we can graph it on here. So if our amplitude is negative, then the y-intercept is a minimum. And if we graph it, we're starting at -1 instead, and then after one full rotation, we are at the maximum. So this is the graph of y is equal to negative cosine of x. So this is probably the most important thing for us to remember. And again, the term amplitude we'll come back to in a few minutes. Now let's look at the sine instead. This is my sine curve. Now for the sine, we are always going to be starting on the y-axis when we are on the middle line, right? So we're on this middle line. We're halfway between the maximum and minimum. And this middle line will have a special name in this course, and we'll talk about it soon. And this is called the principal axis. And if our amplitude is negative, let's go see what's happening. If I have instead negative sine of x, then we are still starting at the principal axis. We're still starting in the middle, but this time we're noticing that it's going towards a negative first. So I'm going towards a minimum first, and then I'm going back up. So this is the curve y is equal to negative sine of x. So the amplitude is negative when the function goes towards a minimum. Okay, now let's understand all these keywords that I just threw at us, amplitude and principal axis. For both a cosine and a sine curve, they have the same behavior. Both of them are oscillating repetitively, where we have a certain maximum that's being repeated and we have a certain minimum that's being repeated. The middle line, like I mentioned, is called our principal axis. And this is exactly halfway between our maximum and minimum. Then we have another key term, which is called the amplitude. Now, the amplitude is going to be the distance from our middle to our maximum. So this amplitude basically is stretching our curve up and down. So we call this the vertical stretch of our curve. And this is the term for A. And like we mentioned, if the A is negative or positive, that has some effect on how the graph looks like. But the actual value of an amplitude is always going to be positive. So this principal axis, basically what it does is it moves our graph up and down, right? So we're moving it up and down without stretching it, right? The A is stretching the graph while the D is just moving it up and down. And the equation of our principal axis is always going to be, because it's a horizontal line, the equation is going to be y is equal to a number, which is going to be the value of D. Now, the next very important parameter is how long does it take to do one full rotation? One full rotation can either be from the middle line going up and down and back to the starting point. This is one full rotation. And the time it takes to complete one full rotation is called a period. So I'm going to write this down here. Now the period can look like I just mentioned, from the middle all up, down, and back to the middle. Or if we look at a cosine graph, it can start at a maximum, go all the way down to a minimum, and back up to the next maximum. That would also represent one period. So we start at the top, we go down to the minimum, back to the top. That would be also one period. Or if we start from a minimum and go up to the maximum and back down, all of these represent one rotation, and the time it takes for that rotation is our period. Now what you'll notice is that in our traditional way of writing a sinusoidal function, this b value is not the period. This b value is always going to be equal to 360 divided by our period. So it's not the actual value of the period, but 360 divided by b. I know this video is very heavy on the behavior and how to write the sinusoidal function. The next video is going to be about applications. But let's try to understand everything that we've learned so far in two examples. So we can write either our function as a sine of bx plus d, right? Or we can write it as f of x is equal to a cosine of bx plus d. Now, the a, b, and d's in both of the equations represent the exact same parameters. Let's look at our first example. So you can find this example. Find the function shown in this graph. The very first thing we want to do is look at the y-axis. And we see that the y-intercept is a minimum of our function. So if it's a minimum of my function, that means I'm going to be using the cosine because we're dealing with a minimum. And because it's a minimum, I know that my amplitude is going to be negative. So these are two things that we're going to have to keep in our back pocket. Now let's go and find the parameters of a, b, and d. First, I like to draw dotted lines where the minimums are and then also where the maximums are. This helps me to find the principal axis, which is exactly halfway in between. In this case, they're telling me that the principal axis is equal to 3. Therefore, the value of d will be 3. Next, let's try and find the amplitude. The amplitude is the distance from the maximum to the principal axis or principal axis to the minimum. So if we have a distance of 3 from the minimum to the principal axis, that means that my amplitude is going to be 3 as well. And now let's talk about the value of b. In order to find the value of b, I need to find the time it takes to complete one full rotation. So I can go from minimum all the way up and back to the starting point of minimum. And I get that my period is equal to 120. Therefore, the value of b is going to be equal to 360 divided by 120. Therefore, the value of b is going to be equal to 3. So putting all this information together, I get that this function is y is equal to negative 3 cosine of 3x plus 3. And you can always test that you did this correctly by putting it into the calculator. So let's put this in the calculator. And when we graph it, it looks similar. I'm just going to change my window because right now my y maximum is going only to 4. But I know that I'm going to have to go at least to 6. And there we go. We see something that is very similar to what I have where I'm starting at a minimum. So I know that I answered that question correctly. Let's do the next question. So find this question in your notes. Find the function shown in this graph. Now again, we have our choices between sine and cosine. The y-intercept is right here. And this y-intercept is definitely not a maximum or a minimum, so that has to be the principal axis. We only have two choices. We either have maximum, minimum, or principal axis. Those are the only y-intercepts we can have. So I know that my principal axis is going to be y is equal to 1. Therefore, the value of d is going to be 1. And I skipped ahead. Because I'm on the y-intercept is the principal axis, that means I'm going to be dealing with a sine function. And on top of that, I know that the value of the amplitude is going to be positive because I'm going towards a maximum first. So positive value for A. Okay, now let's talk about the amplitude. Amplitude is the distance from the maximum to our principal axis. And in this case, we have 1. Now, it's often that these two are equal to each other, but it really doesn't happen all the time. So it's just a coincidence that both examples we did here have the same principal axis and amplitude. They will be different. And then the last one is to calculate how long does it take to do one full rotation. So one full rotation, we can start from the middle. We go up to the maximum, down to the minimum, and back to our starting point. And this takes 180 degrees. Therefore, the value of B is going to be 360 divided by 180, which is equal to 2. So the equation is going to be y is equal to 1 sine of 2x plus 1. And again, you can graph this to make sure that you did it correctly.